Hello there. Today, we are going to be talking about null hypothesis significance testing. Now, null hypothesis significance testing is important to many fields, but I'm going to be focusing on psychology because that is where I have the most experience. Null hypothesis significance testing is a procedure that allows us to make claims about how likely something is. So, looking at our data, how likely is it that the outcome we received is due to chance or not due to chance? And while there's a lot more nuance to that, I'm going to be primarily focusing on the aspect of calculating using null hypothesis significance testing. So what does that mean? Well, first, we need to go through our steps. Our first step is where we choose our hypotheses. Now, there are two parts to this. Part A, we need to choose our alternate hypothesis, which is often referred to as HA. Our alternate hypothesis is typically that x bar is not equal to mu. This gives us a one-tailed version. We could also say that x bar is less than mu, or x bar is greater than mu. And I got those backwards in saying them, but the point stands. We'll go ahead and separate these out in case you come back and look at these. So this would be a two-tailed. And these are one-tailed. And that will become important in a few steps. Now, the next part is that we have to do part B. Here, we're looking at the null hypothesis, often referred to as HO. This is equal to x bar is equal to mu, or there is no difference between the sample we calculated and the population mean. With that under our belts, we can go on to the second step. For the second step, we're going to be looking at choosing our test and our significance level. So how strict are we going to be in accepting and rejecting the null and alternate hypotheses? So first, let's begin with our test. You could use a number of different tests here, but the only one we have looked at in this series that you can use for null hypothesis significance testing is the z-test. So we're going to go for our z-test, which is looking at z-scores. For our significance level, often called a p-value, we're going to set that to 0.05. Now, it should be noted that 0.05 is most common, but 0.01 and 0.1 are also used. There are just different reasons for choosing them depending on what type of research you're doing, how you want to set up your type 1 and type 2 error rates. All right, that takes care of step 2. That out of the way. Let's move on to step 3. In step 3, we're going to be collecting our sample. So let's say we found 35 people that, that are x bar is equal to 72, that the standard deviation is equal to 5, and that mu is equal to 64. That should give us everything we need to go ahead and calculate this. Now we move on to step 4. For step 4, we're going to be identifying our region of rejection. So this is essentially where we take our normal distribution, and that drawing will suffice for now. Not perfect, but good enough for calculating. So we're going to say that since I chose a two-tailed test, up here I chose two-tailed. Where did I put that? Here we go. This is my alternate hypothesis. X bar is not equal to mu, so I'm not choosing a direction. So that means that I'm going to have a tail out to the left and a tail out to the right. So somewhere out here I'll have a tail, somewhere out here I'll have a tail. And in this area beyond, there will be values that give us statistical significance. Now, when we're looking at this, because I chose a two-tailed version at 0.05, that means that I need to split 0.05 in half and put half at each end. So that's going to give me 0.025 in each tail. Now, the z value that goes along with that, the z-score that goes along with that, is 1.96, and over here negative 1.96. Again, remember, the negative just means that the values are below the mean. If I were looking at a one-tailed version, we'll just do a small one over here. Let's see, over here, let's say we're saying that this is mu and that our x bar is higher than mu. So this would be the area where x bar is greater than mu. We'd be putting that whole 0.05 into this bit back here. So to use red again, this whole bit beyond would be red, and we'd have a 0.05 over here, and according to convention we would say that this is 1.64. However, if you look at your z tables, you'll see that 0.16, or rather 1.65, is the same distance away from 0.05. It's just become convention that the lower value, the easier value to meet in terms of significance, is what we've chosen to use. And so when you see a single-tailed test, almost always be 1.64 as the region of rejection for significance of 0.05, or p-value of 0.05. So now we're going to have to move this page away, and we're going to move on to the next page. So now we have step 5. This is where we're calculating our test statistic. So let's write that down. So what does that look like? Well, there are two formulas we can use. We could use z is equal to x bar minus mu over the standard error of the mean. Or if we don't have the standard error of the mean already calculated, we could use z is equal to x bar minus mu over the standard deviation divided by the square root of n. Since I don't have this already calculated, I'm going to go ahead and choose this formula. And let's see how that looks. So we had z, so we don't know what that is yet, so we'll just put that in. X bar, as we saw, was 72, minus mu, which was 64. You can see over here, 64, over our standard deviation, and again, this is for our population parameter, is 5 over the square root of n, which was 35. I'm going to go ahead and condense steps here a little bit. You can go back and watch the videos on how to calculate z-scores if you need a more in-depth version of how to do this. So we're going to have 72 minus 64 is going to give me 8 over, then we'll take care of the square root of 35. 5.92. So 5 over 5.92. Then we'll have to divide 5 by 5.92 is equal to, which is going to give me 8 over 0.84. None of those are high enough to round. Which is going to give me 8 divided by 0.84 is equal to 9.52. Just keeping two values to the right of the decimal. So, given the standard deviation and the values we found in our sample, we obtained a z-score, or rather a z obtained, of 9.52. So we're saying that this is large z, means it's very unlikely that the result we got was due to chance, that there's something acting upon this sample that is causing them to be different from the general population, from mu. And so now we get to go back and look at, well, what was our region of rejection? 1.96. 9.52 exceeds that, so we get to say that we found significance at the 0.05 level, or the p equals 0.05 level if you want to be a little fancier. Now, if we were doing this on a one-tailed test, it's almost identical. If this comes out in the direction we had predicted, it's the exact same thing. However, if we said that, like we showed here, that x bar is greater than mu, and it turns out that x bar is less than mu, we have significance in the wrong direction, which is sometimes referred to as a type 3 error. When that happens, we have to start over. So that means we have to go back to the beginning, change our hypothesis, change the test to the proper direction, collect a new sample, so we can't reuse our sample, and then if we find the same information again, then we can claim significance. And this is important because if we find significance in the wrong direction and then we run a different test on the same data, we're going to end up with a type 1 error rate that is greater than our alpha level or our p-value level, and we don't want that to happen. So it's one reason why we don't see one-tailed tests as much, is that they do have that element of danger to them. They have a lower requirement of proof. 1.64 is easier to get to than 1.96, but there's no danger associated with a two-tailed test in that, well, we're covering our bases in that it could be here or here, and so we don't have any risk of a type 3 error where we'd have to essentially start over. And as I alluded to, step 6 is where we state whether we accept or reject. Reject the null hypothesis, which is also referred to as HO. And there you have it. That is an introduction to null hypothesis significance testing using z-scores. At some point, we'll get into this using a t-test as well, but for the most part, it is the same. So until next time, cheers.